Now we're in the home stretch of Chapter 13. The last two sections are dealing with these colligative properties that I mentioned: freezing point, depression, boiling point elevation, and osmosis. All right, so let's set the stage for this. If we add a non-volatile solute, which means one that doesn't readily evaporate, and we add that to a liquid to make a solution, this extends the temperature range over which the liquid remains a liquid. It basically pushes out both ends of freezing and boiling. So adding a solute to a solution gives the solution a lower melting point and a higher boiling point than the pure liquid would have alone. This is what is known as the freezing point depression. It depresses or lowers the freezing point, and boiling point elevation, it raises the boiling point. Freezing point depression and boiling point elevation are not dependent on what kind of solute you put in there, only on the number of particles that are in solution. So it doesn't matter, for instance, with water. It doesn't matter if I dissolve salt in the water, if I put vinegar in the water, if I have calcium from limestone dissolving in the water. They all have the exact same effect. All that matters is how many particles of salt, of vinegar, of calcium got dissolved in that water. Now, if you have a property that is like that, it's dependent on the number of particles, dissolved solute particles, and is not dependent at all on the type of solute particles. This is the definition of a colligative property. That's what we're talking about. It's just how many particles are in solution that it will have a particular effect. Let's start with freezing point depression. Freezing point of a solution containing this non-volatile solute, one that isn't going to evaporate out, is lower than the freezing point of the pure solvent. This is what we stated. For both freezing point depression and boiling point elevation, the concentration of the solution is usually going to be expressed not in terms of molarity that we talked about with capital M, but in terms of molality with a small m. Okay, molality is the number of moles of solute per kilogram of solvent. So now this is where solvent comes in. I'm not sure why that got orphaned down there, but kilograms of solvent. Okay, so molality is moles of solute per mass. And notice now, this one is not solution, this one is solvent. Now you will not see molality used much within the chemical lab setting, the teaching lab setting, but there are some industries that still use molality. There's still an importance to molality. So it is important to touch on this and to stress this, and it makes a difference whether, what property you're wanting to evaluate, whether you use molarity or molality. So molality is related to freezing point depression, boiling point elevation, colligative properties. Okay, so just a reminder, molality defined with respect to kilograms of solvent, not solution. Okay, so this is the one case where you don't use solution, you use just solvent. So let's say I wanted to calculate the molality of a solution that had 17.2 grams of ethylene glycol, which is C2H6O2, dissolved in 0.5 kilograms of water. Okay, so very simple. I need to know moles of solute, and I'm given grams, so I need molar mass of ethylene glycol. They've calculated it here as 62.08. We get our number of moles, and then plug it in down here, divide by, in this case, not mass of solution, but mass of solvent. That gives us the molality. Now this gets much trickier if you are not given just the mass of the solvent. If you're given the mass of the solution, you may, in that case, have to figure out the mass of the solute and subtract it out. Okay, so be aware, be very careful to see if they are giving you the mass of just the solvent or if they're giving you the mass of the entire solution. Okay, keep an eye on that. Let's say you want to know how the freezing point of something will be affected. So if we have this solution that we made, okay, now it's a little bit different. This was a 0.55 0.554 molal solution, okay, molality. Now, in this case, we've got a little bit more concentrated solution. We have a 1.7 molal ethylene glycol solution, which is automotive antifreeze. And this is the aqueous solution of it. What would the freezing point be? How much would the freezing point be depressed by this amount of ethylene glycol? Now, the formula that relates those is right here. The change in temperature, so the delta right here means change in, okay, so the little triangle here, change in the temperature at the freezing point, so T sub F, is equal to the molality of the solution, small m, times this factor K sub F, okay, it's the freezing point factor for the solution. And you would have to be given that value right here. So in this case, the 1.7 molal solution, number of moles of solute per kilogram, times this K sub F value, 1.86 degrees Celsius per times kilograms of solvent per moles of solute. Okay. That would tell us that the difference is 3.2 degrees Celsius. So if the freezing point of water is normally 0 degrees, then what this does is it buys you 3.2 degrees for the freezing of the water within your automobile system. Now, looking at this one, I just want to show this to you as an example. I will not have you calculate. Your homework may have some of these. You can pull the formula from your book and carry those out. But on a test, I would not be asking you to actually calculate this. I would be asking you to interpret this. So if you're told that the freezing point becomes negative 3.2 degrees Celsius, what's the practical implication of that freezing point depression? That means that the temperature, instead of being right at freezing at 0 degrees Celsius, it's going to have to get below 0 before any water within your automobile system freezes because of the ethylene glycol. That's why it's called antifreeze. It keeps it from freezing up. Okay, so that's the practical implication of it. Same thing when we spread salt on the roads. When you put salt on top of ice, the salt starts to dissolve into the aqueous system. Even though it's ice, it's still an aqueous system. It's just in a solid form. You work that in, and if you get it into a little bit of a liquid solution, it starts depressing the freezing point of that ice. And it buys you usually about 5 or 6 degrees. So that means that in terms of, let's go back to degrees Fahrenheit, 32 degrees Fahrenheit is where we're used to water freezing. That's where you start to get ice on the roads. You can spread some salt on there, and suddenly it's got to get down to about 26, 28 degrees before you'll get any ice. Now, if you have a very, very cold winter and you're dealing with temperatures in the teens or low 20s, spreading salt is going to have a minimal effect. That's where you usually switch to something like sand just to give traction. But if you're trying to melt the ice, you can do that through freezing point depression. All right, now on the other end of things, boiling point elevation. The boiling point of a solution containing a non-volatile solute is higher than the boiling point of the pure solvent, so kind of the opposite of freezing point depression. And this works to our advantage in a lot of ways. So like that antifreeze that we just talked about. In an automobile, not only does antifreeze prevent the coolant from freezing when it gets cold, but it also raises the boiling point. So it prevents the engine coolant from boiling quite so soon if you have a hot climate or in the summer. So it works for us both ways. So you may not think about it that, oh, I need antifreeze in the summer, but antifreeze in the summer actually helps your engine as well. All right, so here's the representation for boiling point elevation, similar to what we saw for the freezing point. So the change in the boiling point is equal to the molality times the boiling point elevation constant for the solvent. Now these constants that we talk about, that K sub B or K sub F, that is something at this point would not have you deriving that. That would have to be a given value, okay? And that could be an empirical value, but basically that's the relationship. So again, I don't necessarily need you calculating that. You'll be doing some in the homework where you have the formula in front of you, but mostly what I want you to look at is the interpretation of what this is telling you. Looking at an example, let's go back to our ethylene glycol. Okay, so it bought us 3.2 degrees Celsius on the freezing end. How much does it buy us on the boiling end? All right, so 1.7 moles of solute per kilograms of solvent. Now, the constant for the boiling point is 0.512, so it's a little bit different here. So the change in temperature is a positive 0.87 degrees Celsius. We would add that to the boiling point. That means that the solution would have to get to 100.87 degrees Celsius to boil rather than 100 degrees. So may not sound like much. It's not as much as we got for freezing point depression. We got 3.2 degrees there. We only got 0.87 degrees here. But when you're dealing with, certain climates, again, that 0.8 of a degree Celsius can be a huge difference. It can be the difference between having your solution boil in your engine and explode your containment there, or keeping it cool enough to keep it going. A couple of other practical applications of these sort of things. There's a very interesting article in your Everyday Chemistry in your book talking about frogs and how they employ antifreeze, basically. So how do frogs winter over? We always see all these frogs that are around all summer long, and they kind of disappear, and then they come back out in the spring, and it's the same frogs. Well, what happens is in the winter, they become frozen, and in the frozen state, a frog has no heartbeat, no blood circulation, no breathing, no brain activity. For all intents and purposes, it looks like they're dead, but you thaw them out, get them warm enough, within 1 to 2 hours, all these vital functions return, the frog hops off like nothing ever happened. So what's going on there? Why are they not freezing to death like other animals? Well, that's because the fluid in the frog cells have a high concentration of glucose, so it acts kind of like antifreeze. It is a solute. It's dissolved in there, in their system. It lowers the freezing point. So their intercellular fluids actually remain liquid down to a temperature as low as -8 degrees Celsius, which if you convert that to degrees Fahrenheit, you'll see that's pretty cold. And for the more temperate climate that we live, we rarely get that cold. So as long as it doesn't get below -8 degrees Celsius, the fluid in the frog still is in a liquid state, and it still allows it to maintain everything, and they just go into sort of a hibernation state. Really interesting. All right, and then the last topic we want to talk about here is that of osmosis. Why you don't want to drink salt water. So you've probably heard this, and if you're ever trapped at sea, out on a lifeboat or whatever, you can't drink the seawater. It will make you sick, and it would eventually kill you if you kept drinking it. You have to find another way to purify water. What's going on in this situation is osmosis. And osmosis is the idea that solvent will flow from areas of high concentration to low concentration. Okay? So if a solution has a high concentration of solute, what it will do is draw solvent from solutions containing lower concentrations of solute to try to even out the concentration. So solvent goes from areas of low to high. Okay, so what is it about seawater? Well, seawater is what we call a thirsty solution in terms of osmosis. It's high in dissolved solutes, in particular salt. So if you drank seawater and it flowed through your body, the stomach and intestines, what happens is you have a higher concentration of salt in the seawater. It's trying to lower its concentration, so it needs solvent. It's going to draw that solvent, that water, out of your bodily tissues. So instead of hydrating you, it's dehydrating you. It's drawing the water out of you. And we can actually use that idea. It doesn't work too well for us with seawater, but we can use the idea of osmosis to our advantage in several ways. So if we look at something called an osmosis cell, It allows water to flow through what's known as a semi-permeable membrane. It allows solvent particles such as water to go through that are smaller, but larger particles such as solutes, salt, ions cannot go through the membrane. And so the water can flow from a less concentrated solution into a more concentrated solution. And if we don't do anything to change that, if we just put it in this cell, and we start it out where the levels of the two solutions are the same on both sides of the osmotic cell, but we have a higher concentration of solute on one side, okay, where the red molecules are indicating water, the blue ones are the solute. What you will see over time is that the water seems to spontaneously come up over here on the side that had the higher concentration. Fluid rises in one side of the tube, and just until the weight of the excess fluid creates kind of an equilibrium of pressure and it stops the upward movement. Okay, so this pressure is known as the osmotic pressure of the solution. Osmotic pressure is a colligative property, just like freezing point depression and boiling point elevation that we've been looking at. It doesn't matter what kind of solute you're looking at, only on the concentration of the solute. The more concentrated a solution, the greater its osmotic pressure will be. Now, what does that mean in terms of practical applications? Well, living systems have figured this out a long time ago, and membranes in living cells are these semi-permeable membranes. They're like little osmotic cells. So if you put a living cell into seawater or salt water, it loses water through osmosis and it will become dehydrated because it's got a semi-permeable membrane. You can look at this by putting blood into salt water. So if you look at this, you have a static figure of this in your book, page 472, figure 13.11, but I like this motion version much better to kind of see what's going on. All right, so when we put blood cells into solutions that have different concentrations of anything, the solution concentration of the surrounding fluid, if it's equal to that within the cell, so there's no net osmotic flow, then you have a happy little cell that has its typical shape. So this is what's known as an isotonic solution that you see here. The flow of water molecules into the cell equals the flow out. The cell just is happy, it's living its own life. But now if I take that cell and I put it into what's known as a hypotonic solution, which is pure water, now the inside of the cell has solute in it. It has a concentration of some kind of solute in it. Okay, so what happens now is the osmotic flow of water into the cell, the water starts to come in trying to equalize the concentration, and the cell starts to swell up, and it could even burst. Okay, so you can see it starting to swell, and it's not real happy there. The opposite, now let's take the cell that's in the isotonic solution and put it into maybe like a salt solution, a solution that's high in solute, known as a hypertonic solution. Okay, again, the higher concentrations on the outside, what it's going to do is start drawing water out of that cell and it starts to shrivel up. Again, not really happy. So these are examples of osmosis. Okay, now we can use different things here. I'll talk about that in a second. Okay, so let's continue on with that. So if you have a solution that has an osmotic pressure that's less than your bodily fluid, okay, that's the hypotonic solution. That would be a hypoosmotic case. Okay, that pumps the water in. And then if you have the pressure greater than that of your bodily fluids, so as in the hypertonic solution, that is a hyperosmotic solution, and that tends to take water out of cells and tissues and dehydrate them. Now, what happens if you're giving somebody an IV, intravenous solution? You've got to be careful to make sure that that solution has the same osmotic pressure as that of the bodily fluids, so that they are isotonic, isoosmotic. If you get that concentration wrong, you're going to kill somebody by either having their cells swell up and explode or dehydrate. So when you give a patient an IV in a hospital, the majority of the fluid is going to be a solution that has 0.9 grams of sodium chloride for every 100 milliliters of solution. That is an isoosmotic saline solution. So that's telling you that's the approximate molality, or molarity. In this case, you've got milliliters of solution. You could calculate what is the molarity of solute in the blood. Now, we're not specifying any particular one in the blood, but we're using sodium chloride because, again, colligative property doesn't matter what kind of solute we use. So we know that sodium chloride is something already in the human body and tends to be fairly innocuous. Okay, so IV is very specific to that. Now, the one other thing I wanted to mention that your book doesn't talk about is using that idea of osmotic pressure to our advantage in something called reverse osmosis. And you've probably heard that term, reverse osmosis, dealing with water purification. I live in a rural area and I have a well, so I actually do have a reverse osmosis system in my home. It works exactly the opposite. What I'm doing is applying pressure. So if we go back, I'm going to skim back on you here for a minute to this cell. If I take this system that's something like this, and now I start applying pressure on this end, so rather than letting the osmotic pressure equalize, I'm going to add my own pressure to it. What I can do is reverse the flow of osmosis, and I can force the water through the semi-permeable membrane over to this side to make pure water, and then leave all the contaminants that I don't want over on this side. But I have to do it through a reverse pressure system. I have to add pressure to it to overcome the osmotic pressure. Okay, just a little side note there is something else that you can do. All right, that wraps up chapter 13 on solutions, and after this we will go back and pick up chapters 11 and 12.